everyone, welcome to Off-Grid Microgrid Controller Explained session. My name is Mohammad Farajullahi and I'm your host today to present the ETAP solution for Off-Grid Microgrid. Through this presentation, I will introduce the Off-Grid Microgrids and the specification and challenges associated with these microgrids. Then we will learn how the ETAP Microgrid solution can be used for Off-Grid Microgrid. Off-Grid Microgrid is a localized microgrid that doesn't have any interconnection with the main grid and should operate independently. Modern off-grid microgrids are suitable to be run as green as possible by using the combination of renewable energy resources and energy storages. During the time when the renewable outputs are high, like the noon time for PV, the energy storages can be charged, and during the peak load hours, the energy storages can be discharged. So this cycle can repeat every day without need for any other resources. However, in these microgrids, the conventional generation like diesel generators can be considered as a backup generation assets in case a failure happens for either renewable energy resources or energy storages. There are several specifications in renewable-dominated off-grid microgrids that needs to be considered to dispatch the assets. In such microgrid, renewable energy resources are not fully dispatchable during the day. For instance, the PV maximum generation happens during the noon, while the PV doesn't have any generation during the night. Besides, energy storages have limited capacity for storing the energy. With that in mind, it is important to forecast the amount of the loads and renewable energy generation ahead of time in order to schedule the right time for charging and discharging the battery. Besides, there are several aspects that are required to be considered to dispatch the assets. For instance, enough reserve margin should be considered for the grid formers. So if an event happens in the system, the grid former can maintain the system frequency and voltage. N-1 contingency or loss of the biggest generation should be considered as a security constraint in dispatching the asset, such that if any failure happened in the system would be able to run and operate without any interruption. In addition, there are other considerations like the SOC balancing among different energy storages and even operation hours of the generators, and these constraints should be also considered in dispatching the assets. More importantly, the economic operation of the asset should be considered in dispatching the asset. Several types of the asset may participate in off-grid microgrid, like the WTG, like the PV, diesel generator, and energy storages. And they may have different costs of operation. So these assets should be dispatched in a way that they incur the minimum cost to the system. In that regard, a microgrid controller is required to dispatch the asset with considering all the aspects that I just mentioned. In conventional microgrids, usually one asset operates in the ISOC mode. In that microgrid, the ISOC asset is responsible for adjusting the voltage and frequency of the microgrid. However, in the renewable-dominated microgrids, renewable asset sizes are pretty large, and they should contribute to the voltage and frequency. And we cannot just pick one asset as the ISOC asset in such microgrids. So usually in these modern microgrids, there are several grid formers, and to get all the grid formers contribute to an events happening in the system, usually the grid formers are operating in the droop mode. Basically, in the droop mode, upon an event happen in the microgrid, the primary controller of the assets will react to that event and change the frequency, change the power of the asset in order to mitigate the event. And it caused the voltage and frequency of the microgrid deviate from the nominal values. So in that case, a microgrid controller is required to adjust the active and reactive power of the assets to maintain the voltage and frequency of the microgrid. Additionally, in the off-grid microgrid, a special restoration and black start is required. Due to the small size of the grid formers in comparison with the size of the transformer and cables, they may not be able to tolerate the inrush current caused by the black start. In that regard, soft energization scheme is being used to ramp up the voltage from the zero to the nominal value to avoid any inrush current during the black start. And after that, the remaining assets can be energized step by step. In that regard, a microgrid controller is required to coordinate the assets in the restoration and the black start mode. With all the specifications mentioned for off-grid microgrids, ETAP Microgrid Controller offers several functions to control and manage the off-grid microgrids. ETAP Microgrid Controller is able to control the active power either through the predefined rules or solving an optimization problem with considering the forecasted values of the renewables and the loads. Also, it can act as a secondary controller in the microgrid in order to adjust the frequency and voltage of the system. Besides, it can perform the black start and restoration of off-grid microgrid based on the scheme defined by the operator. With that in mind, let's go through the ETAP software to learn how the ETAP Microgrid Controller can manage the off-grid microgrids. Here we have an example of off-grid microgrid with 5 MW PV, 2 energy storage, each with 2.6 MW power rating and with the capacity of 9 MWh. We assume that the peak load in this system is around 1.8 MW. Besides, we have 2 DGs that can work as a backup in order to feed the load in emergency cases. One of the key features of the ETAP Microgrid Controller solution is the digital twin. ETAP software provides the digital twin of the microgrid controller within the simulation environment. So basically, the digital twin is not just limited to the microgrid controller. Through the controller element in the ETAP, the inclusion of digital twin for any kind of the controller is possible. For example, if I go in the editor mode, in the instrument, there is an element called controller. If I put one controller inside the project, go inside the controller, in the DLL page, we have the import option. If you go inside the controller folder in the ETAP, there are some built-in functions and built-in controllers for different controller. For example, we have controller for the microgrid controller, we have for the power plant controller, we have controller for the generator, for the energy storage, for fuel cells, for the renewable energy resources, and also for the StatCom. If a user wants to create its own controller, there is an option for the new controller. So basically, the user would be able to create its own controller. So with that in mind, let's now go inside the microgrid controller and focus on that. So if I go inside the microgrid controller that I already created, there are several pages. The first page is related to the controller that microgrid controller is supposed to communicate with them. For example, in this project, the microgrid controller is supposed to communicate with 2 BESS, 2 generator, 1 PV, and there are other controllers like the gateway and PMID that can be used for simulating the behavior of the communication. The most important page in the microgrid controller is related to the DLL page. We can define the settings for microgrid controller and also some system information in this page. Besides, there are several functions in this page. For example, for off-grid microgrids, we have forecaster, we have active power control function, we have reactive power control function, and we have black start. Each of these functions has its own special settings, and the user who is studying the system and doing the simulation needs to go through these settings and tune them. With that in mind, let's go to run some scenarios for this off-grid example. So if I go to the scenario wizard and I select the optimal dispatch problem, we can run the optimal dispatch problem in time domain load flow of ETAP engine. So basically, through this engine, the assets are supposed to be dispatched based on some predefined load profiles and PV profiles for 1 day. Let's run this scenario. The simulation is done. Let's take a look at the result. We can see the result for 1 day from 12 a.m. to the 12 a.m. next day. So at the beginning and midnight, we don't have any PV and we have just a battery. So these batteries are discharged in order to feed the load because they have different initial SOC. So the battery with the greater initial SOC is discharging until these two battery gets to the exactly the same SOC. So at this moment, the battery is trying to feed the load equally, and this discharging continue until the time that the PV is available. So when the PV is available and we have excessive of generation, this excessive of generation is being used to charge the batteries. These two batteries are getting charged until they get to the SOC of the 80%. After that, the batteries cannot be charged anymore, and the power of the PV should be curtailed such that it just feed the load. So this curtailment continue until the load is greater than the PV. So at this time, the batteries also contribute to feed the load. And at the time that the PV is not available, just the battery feeds the load. Let's go through the next scenario, which is secondary frequency control scenario. This scenario is being run in the transient stability engine in the ETAP. So let's run this scenario. So the scenario is done. Let's go through the result. In this scenario, at time 61 seconds, an event happened. This event is a load reduction event. So basically, when the load reduced in the system, the other asset will react to that event. So basically, the PV is trying to reduce its generation. The battery is trying to increase the discharging power. And through these remedial actions from the primary controller, we can see that our frequency, the system frequency, is not going very high, and they can limit it to 100.4%. However, this frequency is still too large, and we need to reduce this amount of the frequency. So microgrid controller is executed every 5 seconds. At the next execution of the microgrid controller, which is around 65 seconds, the microgrid controller will redispatch the PV and the energy storages and reduce the amount of the frequency to 100.2%. But still, we need to decrease this frequency because our threshold, for example, for this system is about 1.1%. So at the next execution, which is 50 seconds, microgrid controller again redispatch the asset, and the final frequency and the steady state frequency would be in the range of the 100%. Let's go to the next scenario. In this scenario, we are trying to simulate the secondary voltage control reaction from the microgrid controller. This scenario is being run in the transient stability. So let's run this scenario. The scenario is done. Let's go through the result. Let's plot the voltage of the main microgrid bus and also the reactive power of the other asset. At time 61 seconds, the voltage reference for the EMGC is being changed to 102%. At the next execution of the EMGC is trying to redispatching the asset in order to reach that voltage for the POM bus. We can see that the reactive power of the PV is being increased, and the reason for that increase is that the PV has more priority than the energy storages for reactive power control. So the reason for reducing the reactive power of the BESS is due to the effect of the droop in the BESS inverter. If we take a look at the result for the bus voltage, we can see that the microgrid controller will try to increase the voltage of the POM bus at several steps at the end of the simulation, or around 1 minute after this change of the setting the voltage. We can see that the voltage of the POM bus get close to the voltage reference sent to the EMGC. The next scenario is the scenario for the black start. The black start is being run in the transient stability engine of the ETAP. Let's run this scenario. Let's go out and plot the result for the bus voltage, bus frequency, and the power of the asset. In this scenario, around t equal to 6 seconds, the system goes to the black and all the inverters trip. After this trip, the microgrid controller will detect the black start in the microgrid. So after some delays, the microgrid controller will try to start the soft energization using the BESS. So basically at that moment, around 25 seconds, the BESS will start the soft energization. You can see the voltage will increase in order to reach the voltage to the nominal value. At this time, so the voltage of the system is 100%, and the frequency of the system also is 100%. So we can try to energize the load. As the next step after this soft energization, we pick up one of the load in the system. So by picking up that load, we can see that the BESS go to the discharge mode and they are trying to feed this load. After some moment, around 50 seconds, we can see that the PV start to ramp up its power generation. So as the PV is increasing its power, we can see that the discharging power of the battery goes down, and it start to charging it until the PV goes to the maximum power generation. So at that time, when the PV is at the maximum power generation and the system is stable in terms of the voltage and the frequency, we can assume that the black start is completed and we can start the normal operation of the system. It's important to mention that the ETAP Microgrid Controller solution is a model-driven technology. Basically, user can first develop and modify all the function blocks, add and change any settings in the controller logic. Then the performance of the functional logic and blocks and all the settings can be evaluated in the software, ETAP software. Once the user is satisfied with the result, the developed function and the settings can get transferred to the ETAP controller hardware to function in the actual system. With that in mind, we can deploy the EMGC control functions with all the tune settings and required system information and import that deploy file in the controller hardware without any further settings and system information setup. To do that, we can go inside the MGC function, MGC controller, go inside the associated page and deploy. Inside the project folder, a file called controller deploy.mgc is created. This file can be uploaded in the actual microgrid controller hardware, and all the functions and settings will be transferred to that hardware. ETAP also offer a web client for the microgrid controller hardware. Through that web client, the user has opportunity to change the setting, check the status of the asset, and also see the value of the meters, and also user would be able to change the operation of this microgrid controller hardware. Through this session, we learn how ETAP Microgrid Controller can manage and control off-grid microgrids, and also we show how digital twin of ETAP Microgrid Controller can be used for the off-grid microgrid study. Thank you so much for attending this session, and please reach out to me if you have any questions.